Today we're going to discuss Optics Notes 2. We're going to continue our discussion of optics. And so with optics, you know that light consists of colors. It consists of other things besides visible light, as we know. But of course we have colors, and the main colors are red, orange, yellow, green, blue, purple. When you talk about light, we're going to have three primary colors, red, green, and blue. You're probably used in your art class that the three primary colors are red, yellow, and blue. And that's the truth for pigments and for your art class. But for when we're discussing light, which is additive light, our three primary colors are red, green, blue, which is why if you see your TV and you know your LED lights, they consist of small red, green, and blue lights. Any other light besides what you see in the rainbow is going to be something that is a combination of different wavelengths. So pink does not correspond to a certain wavelength. Contrasting like red and green. Red and green, I can tell you what the wavelengths of red and green are. You can Google them, the wavelength of red lights. But if you Google the wavelength of pink light, nothing should show up. It should tell you that pink is actually a mixture of two different kinds of lights. It's the mixture of the ends of the red and purple light. If I see red and purple light, I'm getting multiple wavelengths, but my eyes are perceiving it as just pink light. Similarly with white light is the mixture of all the lights. We're getting red, green, and blue all together. This is important to know that colors are different wavelengths because it turns out that index of refraction that we learned last time and is dependent not only on the medium but also the frequency of the light. What this means for us is that red and purple light, different color lights, when they go through a object and have refraction, they're going to bend at different angles, and we call this a dispersion. And so you can see this in a prism. If you ever shine a light at a prism and it transforms into different colors, it's because while the white light is entering in, and we know white light is a mixture of lights, and once it enters in the white light, all the different wavelengths spread out because they all bend at different angles. And so red light bends the least, while purple light bends the most. And so they're all going to spread out, and we get this nice rainbow of colors. And so we can solve a problem with this. We're just going to use our Snell's law, and we're just going to do it multiple times. So if we have a beam of light, a white light that goes into flint glass at an incident of 43.2 degrees, red is going to bend with an index of refraction of 1.662, and violet's going to bend with an index of refraction of 1.698. We just to figure out between the two. And so we can first solve red. Let's write our Snell's law. We know that if we're starting in air at an angle of 43.2 degrees and we're entering index of refraction is this. And so we can find the angle that red goes into it. So I'm going to put theta r to denote this is the angle that red is going to be. And we just 40, which and get that sine of 43.2 divided by 1.662 gives us, I should put sine, my bad, sine of theta r, my bad. I forgot to bring my sign down. We need to keep the sign there. So sine of our angle is going to be equal to 0.41188. And so I can do inverse sine on both sides and see that theta r is equal to the inverse sine of that 0.41188, which is equal to 24.323 degrees. We can do this exact same work for purple. I'll skip a couple of steps here. Our equation is the same though, so I'll rewrite that to start off with. For purple light, the light entering in is the same index of refraction. We have 43.2 degrees, but the difference is that purple light has an index of refraction of 1.698 when it enters. And so we're going to look for the angle of the purple light. In the end, if you solve it, you're going to solve the exact same way. It's the same math involved. You should get, let me go ahead and solve it. Divide by 1.698. And then do inverse sine on both sides. And we get 23.775. And so when you subtract those two, you get a difference of 0.548. Now more than ever, it's important that while you're doing the work in your calculator, you're keeping as many decimals as possible and you're keeping your answer as accurate as possible. Don't round in your work. You can round when you're writing it down. So what I mean is when you're writing it down and you're kind of doing the work on the paper, you can write it, you can abbreviate or you can round just so you're not writing as much. But in your calculator, you should always be using exact values. And so you should have hopefully a good enough calculator that you can store values into numbers, or you can go up and like copy and paste numbers. And that's what you should be doing. You should be taking the exact values you had before and moving them now. That way we get a more precise answer. If you round, your answer is going to be a bit off by quite a bit. Okay, next we have something called polarization. All EM waves, all light, and both non-visible and visible light, are electromagnetic waves. And we know that already, but what does that even mean? Well, we haven't talked about it yet. What it is that electromagnetic waves, light, consists of magnetic and electric fields propagating up and down and side to side. And so you can kind of see a picture here. That's really what light is. It's these electromagnetic fields propagating, and that's really what the transverseness of the wave is. It's these fields that are vibrating. And we call polarization. Polarization refers to the direction the EM wave propagates. It specifically refers to the way the electric field propagates. And so you can see in this image, this electric field is moving up and down. And so we say that the polarization of this light is up and down. That's the direction of the polarization. And every single wave, light wave, is going to have a certain direction that it propagates. Okay? However, if we get light sources, kind of like the sun, a light source generally does not send waves only in one direction. It sends a bunch of different waves out at once, which is why the sun is so bright, because it's sending multiple waves, tons of waves out at once. And all these waves that it sends out are all different, they all have different polarizations. They're all vibrating in different directions. They're all, the direction of the polarization of each individual wave is not consistent amongst them all. So we call it unpolarized when we have a mixture of different polarizations. But we can polarize it if we send it through a polarizing filter. If we get some sort of filter that distinguishes between lights, and the best way to see this is if you have polarized sunglasses, those are polarizing filters. What they're doing is they're only allowing certain polarized directions of light to get through. And so you can see if we have a vertically polarized filter here, it's only going to allow light that's propagating vertically, or at least that light that has a vertical component to it. Okay. And so if it's like at an angle, it'll just diminish the amount of light that it gets through. It won't just cancel completely. But if they're completely perpendicular, like this light that's propagating up and down here, let me turn off my notifications, sorry. As it goes through there, and it goes to a completely horizontal, now that they're perpendicular, it's not going to let any light through. And so the light that goes to the end is going to be zero. We're not going to get any light that goes to the end there now. And so sunglasses do this. They're going to polarize your light, at least if you have polarized sunglasses, and that's how they diminish it. And we have an equation that describes this. This equation, this is the intensity of the light that's going before the filter, because we know I naught, when we were talking about like V naught was always before, while V was always after. So this is the intensity of the light beforehand, this is the intensity afterwards, and this is the angle between the two. Okay? So if I have a light that's propagating this way, and I have a filter that is filtering light this way, so it kind of looks like a filter like this, okay? We're looking for the angle between these two, and so the angle between this and the angle between that is whatever angle that is, and that's what theta you're looking for. The angle between the direction polarization and the filter. So we can look at a couple examples of this. If we have completely polarized light of intensity 150, and it's going through a polarizing filter that's at an angle of 89 degrees, we can figure out what intensity we're going to get afterwards. And we just throw it into the equation. It's pretty simple. The important thing to note here is this cosine squared. If you've never seen this before, cosine, when we write it like this, What this is saying is we're just taking cosine theta and we're squaring that. And so it's just kind of a weird way of writing. Take cosine of theta first, plug in your number for 8, so plug in 89, and then after you get a value, cosine of 89, square that number, okay? And so if I take 150 in my calculator, so really in my calculator I'm going to type this. I'm going to do 150 cosine of 89, and then I'm going to square that number. So I'm going to do 150, open parentheses, cosine of 89, close my parentheses, and I'm going to square that. You should get this. So make sure you're plugging it in. We're only squaring this. We're not squaring the 150. We're only squaring the cosine of 89. And so specifically cosine of 89 was 0.0174. And so you should be squaring that value, which gives you like 3 times 10 to the negative fourth-ish. And then you're multiplying that by 150. And you get this number here. And that's our new intensity. Another kind of question, a bit different way to write it, is what angle is needed between the direction of polarized light and the axis of polarization filter to reduce the intensity by 90%? So first of all, if we're reducing by 90%, that means afterwards, after we go through the polarizing lens, we're going to have 10% of the light left, right? If we have a 90% off sale, that means we only have to pay for 10% of the original price. So 10% is really the number we're concerned with. And we know the decimal way of writing this is 0.1. And the way we plug it into the equation is we just think about writing percentages as their decimal form. What we're saying is afterwards we had 10% of the light, so we're going to plug that in for our intensity afterwards. We're going to plug in 0.1 here. So the question is, what do we plug in for I naught then? Well, afterwards we had 10%. Beforehand, we had the original value. Well, the original value of something is always 100%. You always have 100% of something, and then you edit it, and you get 10% of it, or you can have greater than 100%. You can have more, like 150% of something. But our original value is always 100%, which we write that as just the number 1. And so you can put 1 here. And then we solve. But of course, 1 times anything is just a thing, so it's the same thing as doing 0.1 cosine squared theta. To undo this, again, this cosine is the same thing as writing cosine theta squared, if you haven't seen it before. And so we want to get rid of the squared first. We want to take the square root of both sides to start off with. So square root of 0.1 gives us 0.316 is equal to cosine theta. And we can do the inverse cosine of both sides and get that cosine, or we can do theta is equal to 71.57 degrees. Last thing we're going to cover real quick is images, and specifically we're going to talk about plane mirrors today. Things you need to know is you need to know that when we reflect off surfaces, our incidence angle is equal to reflection angle. We already talked about that. That's saying that whenever we reflect off a light here, these angles, our incident angle is equal to our reflection angle. Something we already talked about. But now we also know that if we're in a flat mirror, our image, which is the thing that it look like when you look at a mirror and you see something that looks like it's behind the mirror, that's your image. It looks as if this thing is behind the mirror, so that is our image. And we know that the distance that the image appears to be behind the mirror is going to be equal to the object's distance. So you can see that they're equal. This negative sign just denotes the direction. And so that this distance, it's behind the mirror, therefore it's negative as compared to being in front of the mirror where it's positive. Just a fact, your image is called a virtual image, and it's because obviously that image is not real. Light does not go here. Light cannot pass behind the mirror. It's in front of the mirror. Later, we will see real images. We will see where light actually does converge in front of a mirror. And so we will get real images in other kinds of sources. But in this case, virtual images is what we're getting behind the mirror because the light rays do not actually converge there. What we need to do, though, is we need to be able to sketch we need to be able to do ray tracing. And so go ahead and get a blank sheet of paper and sketch this. You might want to use like half a sheet of paper and sketch a blank area on the left side where you can do some sketching over here, leave it blank. And then on the right side, draw an arrow. You can actually really put it wherever you want. You could just put it randomly on the other side and then put a dot somewhere. So you can do it differently than me, but I'm gonna work like this. And if you wanna kind of copy more relative to me, stay on track, you can. And we're gonna discuss, we're gonna do something called ray tracing. We're gonna get the exact direction, the exact way the rays are gonna go from this light source, because light's gonna start at an object and bounce to an observer. This dot is our observer. It's what's receiving the light. It's kind of like if you were standing there, that's your eyes. It's what's observing the light and receiving it. Okay? The first step is we need to use this property where, whoops, the image distance is the same thing as the object distance. And so if this is our object, we know that whatever this distance is going to be equal to the distance over here. And so you actually need a ruler for this. And so if you don't have a ruler, go ahead and grab one. If you don't have a ruler, print one out. You don't necessarily need to have an exact ruler. So if you print it out and it's off, that's okay. It just needs relative distance. And so, but you do need something to measure with so that you can get some exact values. And so I'm actually going to try to do this on my screen the best I can. Measuring from 10, about 16.4. So I'm going to measure 16.4. And I'm going to sketch to 10. And that's where I'm going to put my dot. And then I'm going to do the same thing for this bottom one. I'm going to measure. I'm going to reflect these two dots. I'm just going to reflect the top and the bottom of the arrow across the line, and you'll see you get a pretty good reflection if you do that. So the first step to do our ray tracing is draw the image using a ruler and getting it perfectly mirrored across your mirror. Second thing you're going to do is you're going to draw image rays. Okay? And so I'm going to basically draw straight lines from here to the dots over here and here. And so all I'm just going to do is get a straight edge. You don't need to actually measure anything. You just need a straight edge. I'm going to sketch these lines in. And this is what light appears to be doing. It appears that light is going from this image, which is behind the mirror, to your eyes. That's why in the mirror, it looks like there's an image behind the mirror, because this is what the light appears to be doing. But what's really going on is step 3. Draw the object rays. And all we're going to do is take these points where the mirror intersects, and we'll connect the dots to our original object. And that's it. That's all there is to ray tracing. These should be complete. I guess I just skipped a line. But that's all it is. And so you can kind of see that if we are light starting at the object, it's going to travel this way. And then it's going to reflect off the surface and travel this way. And that's all there is to ray tracing. You don't have to put those arrows in, but I'm just showing you the path the light would take. And you can do the same thing for the bottom. Next time we will get into spherical mirrors and some lenses, and we'll do some other stuff. Although next class we'll actually be doing a gizmos, so you don't need to come to lecture or watch the video next time. We'll just be doing gizmos so that you can do online. The following class, we'll get back into some notes. With that, have a nice day.